In this lesson, we will learn two techniques for solving two equations with two unknowns. These are often referred to as systems of linear equations. Now, a linear equation is an equation that can be written in the following form, and a system of linear equations is a pair of two linear equations. So, for example, this is a system of linear equations. Notice that we have two equations here with two variables, x and y. To solve this system, we must find a value of x and a value of y such that both equations hold true. Now, on their own, linear equations have an infinite number of solutions. For example, here are just a few solutions to the top equation, and here are just a few solutions to the bottom equation. We are looking for the one solution that both equations share. In this example, they share this one solution. So the solution to this system of equations is x equals 5 and y equals 2. Okay, now let's learn two methods for finding solutions. The first method uses substitution. So to solve this system, we must first take one of the equations and solve it for one of the variables. Now, it doesn't matter which equation we choose, and it doesn't matter which variable we solve for. However, it is a good idea to choose an equation that is relatively simple to solve for one of its variables. In this example, it is easiest to take the top equation and solve for y. When we do this, we get y equals 17 minus 3x. Now that we know that y equals 17 minus 3x, we can take the y in the second equation and replace it with 17 minus 3x. When we do this, we see that we now have an equation with just one variable, which we can solve for x. To do this, we'll first expand the left-hand side, and then we'll simplify the left-hand side. From here, we'll add 34 to both sides, and then we'll divide both sides by 8 to get x equals 5. Now that we know that x equals 5, we need to find the corresponding value of y. To do this, we can take any of the above equations and plug in 5 for x. So let's take this equation here and replace x with 5. When we evaluate this, we see that y is equal to 2. So the solution to this system is x equals 5 and y equals 2. Okay, let's summarize the steps involved in the substitution method. First, choose an equation and solve it for one variable. Then take the other equation and replace the chosen variable with its equivalent expression from the first equation. Then solve for the variable, and plug the solution into the equation to solve for the other variable. Okay, now let's examine another technique called the elimination method. This technique relies on the following properties. First, if a equals b and c equals d, then if we add the left-hand side and add the right-hand side, the results will be equal. Similarly, if a equals b and c equals d, then the difference on the left-hand side will equal the difference on the right-hand side. Okay, let's see how these two properties can help us solve systems of equations like this one here. Notice that in the top equation here we have positive 3y, and in the bottom equation we have negative 3y. Given this, notice what happens when we add the left-hand side and add the right-hand side. First, 2x plus 4x equals 6x, and next we have positive 3y plus negative 3y. When we add these, the y's cancel out. They have been eliminated. Finally, we have 10 plus negative 16, which equals negative 6. At this point, we are left with one equation with only one variable, which we can solve for x. When we divide both sides by 6, we see that x equals negative 1, so we already have half of our solution. Now that we know the value of x, we can plug this value into either equation to find the value of y. Let's use this equation, since its numbers look a little more manageable. So when we replace x with negative 1, we get an equation we can solve for y. First, we'll simplify the left-hand side, then we'll add 2 to both sides, and finally we'll divide both sides by 3 to get y equals 4. So the solution here is x equals -1 and y equals 4. Let's try another question. In this example, the coefficients in the two equations will not allow us to eliminate a variable by simply adding or subtracting the two equations. However, if we take the top equation here and multiply both sides by 2, we get the equivalent equation 6x plus 4y equals 18. Now, if we take the bottom equation and leave it as it is, we now have 6x in the top equation and 6x in the bottom equation. So if we subtract the two equations, something nice happens. First, when we take 6x and subtract 6x, the x's cancel out. Next, when we take positive 4y and subtract positive 5y, we get -1y. And finally, when we take 18 and subtract 15, we get 3. At this point, we can solve this equation by dividing both sides by -1 to get y equals -3. Now that we know the value of y, we can plug this value into any of the above equations to find the corresponding value of x. Let's use this equation. So when we replace y with -3, we get an equation that we can solve for x. First, we'll simplify the left-hand side, then we'll add 6 to both sides, and finally we'll divide both sides by 3 to get x equals 5. So the solution here is x equals 5 and y equals -3. Okay, let's try one more. To solve this one, let's first take the top equation and multiply both sides by 3 to get the equivalent equation 6x minus 9y equals 3. Next, we'll take the bottom equation and multiply both sides by 2 to get 6x plus 14y equals 26. Since we now have 6x in the top equation and 6x in the bottom equation, we can subtract the two equations in order to eliminate the x's. So when we subtract 6x minus 6x, the x's cancel out. Next, we have -9y minus positive 14y, which gives us -23y. Finally, when we subtract 26 from 3, we get -23. At this point, we can solve this equation by dividing both sides by -23 to get y equals 1. Now that we know the value of y, we can plug this value into any of the above equations in order to find the value of x. Let's use this equation. When we replace y with 1, we get an equation we can solve for x. First, we'll simplify the left-hand side, then we'll add 3 to both sides, and finally we'll divide both sides by 2 to get x equals 2. So the solution here is x equals 2 and y equals 1. Okay, let's summarize the steps involved in the elimination method. First, manipulate the equations until you have matching coefficients that will allow you to eliminate one variable. Then add or subtract the two equations to eliminate that variable. From here, solve for the remaining variable, and then plug the solution into any equation to solve for the other variable. Okay, now that we have two techniques for solving systems of equations, which method should we use when presented with a system? For example, which method should we use here? Well, in this example, adding or subtracting the equations will not eliminate a variable. However, notice that the top equation here can be easily solved for y. At this point, we can take the y in the bottom equation and replace it with 4x minus 1. Okay, how about this example? In this example, we have -3y in the top equation and positive 3y in the bottom equation. So if we add these two equations, the y's are eliminated, leaving us with an equation we can solve for x. Okay, let's summarize. In this lesson, we learned two techniques for solving systems of equations.
Now we'll talk about the three equations with three unknown case. The very first thing I'll say is that this is an awfully rare scenario. It's unlikely, unless you're doing very well, that you're going to be handed something like this. But it could show up, so it's worthwhile talking about this. So, suppose we have this particular system. We have 3 equations and 3 unknowns. Now, of course, I haven't given a question here, but let's just assume that for whatever reason, we need to solve for the individual values of all 3 variables. Well, a few thoughts first of all. Big idea number 1, if the number of equations is fewer than the number of variables, you will not be able to solve for the individual values of the variables. If you have 2 variables and only 1 equation, you can't solve for those individual values. If you have 3 variables and 2 equations, you can't solve. In order to solve for individual values, you need to have 3 equations with those 3 variables. Big idea number 2 is quite subtle. Depending on what the question asks, you may not have to solve all the way. Now this is tricky. Sometimes the question will say, what's the value of x? What's the value of y? They'll want to know a specific variable. Sometimes, though, they'll ask about an expression. What's the value of x plus y? What's the value of x minus z? What's the value of x plus y plus z? Something like that. Often when the test does that, there's a much shorter way to solve directly for the value of the expression without solving for the individual values of the variables. So always keep your antenna up for these kinds of shortcuts. If you can go directly to the answer without doing all the work of solving all the equations all the way, by all means do so. Finally, big idea number 3, inside every big problem is a little problem struggling to get out. Now, of course, this is kind of a playful way to say it, but it turns out in mathematics, much of mathematic problem solving consists of reducing problems you don't know how to do to problems you do know how to do. Now, this is true not only at the level of the test, but even at the level, say, of calculus and beyond calculus analysis, topology, even all the way up to PhD levels in mathematics. The way that new math gets done at the PhD level is that mathematicians are reducing problems that we, the human race, doesn't know how to do, reducing them to problems we do know how to do. So it turns out this is a very sophisticated strategy, and it's a very important perspective in your problem-solving abilities on the test. Now, in this particular case, I'll show you what I mean. So here we have 3 equations with 3 unknowns, and I've labeled the equations. Well, theoretically, you've watched these videos, and so you know how to solve 2 equations with 2 unknowns. That we've covered already. So now we want to know how to do this. So what we're going to do is take a series of steps that will allow us to change 3 variables with 3 unknowns into 2 variables with 2 unknowns, because that's something we know how to do. Well, first thing that catches my eye, notice we have a plus x and a minus x. That really just kind of jumps out at me. It's kind of a screaming sign as far as I'm concerned in these equations. What that means is I could add those 2 equations and eliminate an x. So I'm going to add b and c. b is 2w plus x minus 4y equals negative 14. c is 3w minus x plus 2y equals 8. Add them up, add everything straight down, we get 5w minus 2y equals negative 6. I'm going to call this equation D. This is now one equation that has 2 unknowns. So by itself it's not very useful, but if we could get another equation with the same 2 unknowns, then we'd be in business. So we want to pick another pair of the 3 original equations, a different pair, so not B and C this time, a different pair, and see if we can eliminate x again in this new pair, because if we eliminate x again, we'll get another equation that has just w and y in it. So again, this plus x looks like it would be pretty easy to cancel it with this minus 2x. If I just multiply b by 2, then that should be able to cancel them. So I'm just going to have a by itself. A is w minus 2x plus 3y equals 13. I'm going to multiply 2 times b. So everything on both sides of the equation gets multiplied by 2. Of course, you're always allowed to multiply both sides of an equation by the same thing. That's perfectly legitimate. That will give me 4y plus 2x minus 8y equals negative 28. All right, so very good. So now, again, add straight down. I get 5w, the x's cancel as predicted. I get negative 5y equals negative 15. Now, ordinarily, I would say, gee, all of these are multiples of 5. Wouldn't it be easier to divide by 5, get smaller numbers? Then that might make it very easy to cancel, to substitute, to do all kinds of things. But I'm not going to do that only because, I'm going to call this equation E as is, only because I notice I have a 5w here and a 5w here. Wow, those are kind of screaming out to me now. Can I just solve for 5w for both of these equations? 5w equals 2y minus 6. 5w equals 5y minus 15. So if these two things both equal 5w, they must be equal to each other. So this is an example of substitution. We're going to set these equal. 5y minus 15 equals 2y minus 6. Well, now I'm down to one equation with one unknown. This is great. I know how to solve this. So subtract 2y from both sides. We get 3y minus 15 equals negative 6. Add 15 to both sides. 3y equals 9. Divide by 3. We get y equals 3. Okay, and of course we know with the two unknown case, once we get the value of one variable, we just plug it in. We could plug it into this one or this one, doesn't matter. This one looks like it has smaller values, so I'll just plug it in there. 5w equals 2y, which is 6, minus 6, equals 0. That's funny. If 5y equals 0, 5w equals 0, that means that w must equal 0. Okay, very interesting. That can happen sometimes. W equals 0. So now I have the value of w, the value of y. I'm almost done, but I need the value of x. So now I actually have to go back to one of the original equations. Let's take the top one, a. W, that's 0, minus 2x plus 3y, so 3 times 3 is 9, equals 13. Subtract 9 from both sides. I get negative 2x equals 4, or x equals negative 2. And those are the three values of the three variables from these equations. Again, notice that the strategy I used was to reduce the 3 equation 3 unknown scenario to a 2 equation 2 unknown scenario. So just to summarize, first of all, I'm going to pick 2 of the 3 equations, and using either substitution or elimination, eliminate one variable. Incidentally, 99% of the time, it's going to be much easier to use elimination rather than substitution. Then I'm going to pick another pair of those original equations and similarly eliminate the same variable. So at this point, I will be down to the 2 variable with 2 equation case. Now, just use the 2 equations with 2 unknown techniques. We've learned those already. Solve for those 2 variables. When you have the numerical values of those 2 variables, finally, plug into any of the original equations to find the value of the 3rd variable. This is exactly how you solve this scenario.